To Industrial Engineering 537, large-scale systems. We're continuing now in the series of course material on modeling and analysis. We've been through system of systems modeling. We've been through intelligent agents. And another very important aspect of large-scale systems modeling is that of risk analysis. So again, in continuing the spirit of having subject matter experts here, we have our subject matter expert in the area of risk analysis with us today. He's going to spend the next 2 or so lectures telling us about the fundamentals of risk analysis. So let me introduce Dr. Greg Weiss. Dr. Weiss is a distinguished member of our technical staff at Sandia National Laboratories. Greg has his bachelor's, master's, and PhD, all in nuclear engineering, from the University of Illinois. Dr. Weiss has worked in the areas of risk, reliability, and vulnerability assessment at Sandia for more than 20 years. During that time, he's performed risk assessment studies for nuclear reactors, space vehicle launches, nuclear test facilities, telecommunications facilities, and a variety of other high integrity and potentially high consequence systems. He's also developed risk and vulnerability assessment and uncertainty analysis methodologies for a very broad range of applications. He's expertise in the areas of fault tree analysis, event tree analysis, security vulnerability analysis, integrated risk uncertainty analysis using Latin hypercube sampling and other techniques. Dr. Weiss has taught short courses on these subjects for more than 14 years, so he's an excellent resource for us in this class. Dr. Weiss's current responsibilities include development of security risk assessment methodologies for evaluation of high security nuclear facilities. Research interests include assessment of pre-attack planning, insider threats, decision support, and synergistic effects between cyber and physical security systems. That should be near and dear to many of you. I know that many of you do have on the job responsibilities for right now for computer cyber systems. So Greg is a good resource for that as well. His research interests also include object-oriented techniques for risk, reliability, and vulnerability analysis. He holds a patent for a method to analyze complex, non-planar, and arbitrarily interconnected telecommunications networks. Dr. Weiss is chair of the Power Systems Working Group for the Mars Science Laboratory Interagency Nuclear Safety Review Panel, and a member of this panel for the Pluto New Horizons mission. This group has responsibility for estimating the potential radiological releases from a radioisotope thermal generator as a result of a launch accident for each nuclear-related space mission. This is important work. The White House used this panel's report as the basis for its launch authorization decisions. I could go on, but I'm going to stop at that point and introduce Professor Weiss. Greg?
Thank you, Dennis. One of the things that has always really intrigued me about risk assessment is the huge variety of domains where it's applicable. So today I want to talk a little bit about what risk assessment is, how we go about doing it, and then give you a flavor for some of the variety of techniques that are used and some of the domains where it's applied to give you an idea of that breadth and help you to apply it in whatever part of systems engineering you find yourself working. What we're going to talk about today is some overview, some definitions, the terms, how we talk about risk assessment, the basic principles and techniques, and then I'm going to spend probably about 60% of the lecture talking about example applications and then some additional techniques as we discuss that, and then a little bit at the end to give you a flavor for some of the software that's available to help you with risk assessment. So let's start out talking about what risk assessment is. There's a lot of different definitions out there. Most of them are pretty similar in that they talk about risk as the potential for realizing unwanted or adverse consequences. it revolves around three fundamental questions. What can happen? How likely is it? And how bad is it? We can translate that into what scenarios can happen to our system, and how likely are they? What's the frequency of those? And what are the consequences of those? Really, some of the earliest risk assessment work was done in the area of the insurance industry, and they always aggregated things in terms of an annualized loss expectancy. So, for example, your automobile insurance policy, the insurance company is looking at how bad is it, what's the level of loss that they will expect for a given accident, how likely is it, how many accidents occur in a given year, and what can happen, what kinds of accidents, and they're writing their insurance based on that. They'll take all of that information and aggregate it into an annualized loss expectancy where they add up the frequency times consequence for each one of those, and they can use that to set their insurance rates. The objectives of the risk assessment are really to understand the system and its operation, understand it well. So we need to understand what consequences can occur for any system, be it a system of systems at the large-scale complex level, or even down to a single decision we're making in our homes. How severe are those consequences? How likely are they? What are their root causes? And then getting into what are we relying on to prevent them. The objective of risk assessment is first to understand them, but then to understand the existing risks, then to understand the types of options there are for changing the system or changing operations in order to improve the system and its operation to reduce risks in a cost-effective manner. So we can do that looking at reducing the magnitude of the consequences, or we can reduce the likelihood. We may be able to eliminate some scenarios altogether. And then we need to look at it from a cost perspective. Is it worth it, or do we just want to accept those risks and move on? The ultimate objective of risk analysis is always to support some sort of decision, whether that's a decision to accept the risks as they are, knowing them, maybe buying insurance, or whether that's a decision to change the system and work into some new areas to improve the system in a cost-effective way. Risk assessment, risk analysis, is not a cookbook. Instead, it's a process for disciplined investigation. I can't tell you a series of steps to say if you always do risk assessment using this 1 to 5 checklist that you're going to have a good risk assessment. Rather, you have a toolbox of different methods that support discovery. You're trying to discover, again, the scenarios, what can happen, discover the likelihood of those scenarios and how bad the consequences are for them. The key here is completeness. If we're going to understand all of the risks associated with the system and to make intelligent decisions on what to do about them, we need to understand what that universe of possible scenarios looks like. So we may not need to understand every single scenario. In fact, we probably can't. There are probably too many scenarios. But we need to understand what that universe looks like, all of the different types of scenarios, along with their consequences, and we need to support them in enough detail to support well-informed decisions. So because of that, every analysis we do is going to have a different level of detail. In some cases, we may only have to look at a couple of scenarios, and we look at them in great depth in terms of their likelihood and complexity. In other cases, we may look at such a wide variety of different scenarios and look at them only superficially. We will trade those off to get enough information to support well-informed decisions. And that's why part of this is a science and part of it's an art. There's an art in knowing what the appropriate level of detail is to support specific decisions that are being made, while the science is being systematic in the understanding of how the system works, being realistic in understanding the scenarios, the likelihoods, the consequences, and putting good science behind that wherever possible. So it's part art, part science, and there's experience and talking to other risk assessment people, talking to the decision makers will help you know where to stop and where to dig deeper. And it's an iterative process in order to understand that. you may not be able to see this one very well. It is kind of an eye chart, but I wanted to give you an idea of some of the domains where risk assessment is important. We're talking about the potential for realizing unwanted consequences, and it's always the same three questions. What can happen? How likely is it? And how bad can it be? Whether it's regarding security analysis, whether it's project management, financial instruments, and you can look at this later, but I have examples on a lot of these coming up later in the lecture. The key is that we're using the same methods to look at all of these different areas from the perspective of, do we understand what the potential risks are, and how can we mitigate those risks? What will be cost effective in mitigating them? I want to talk about some definitions now. One of the things about risk assessment that's been very frustrating is that the definitions that you will read in many different textbooks are different for some of these terms, and in fact, in some cases, contradictory. So I have some working definitions up here that will work for us, and just realize that as you talk about consequences or threats especially, or scenarios, that those words may mean different things to different people, and so you may have to explore that a little bit. So when we talk about the what can happen, what is a scenario, we're talking about an outline or a synopsis of events here. Likelihood, the key is to understand is that we have an uncertain future event, something that may or may not happen, and so likelihood represents the degree of confidence or certainty that we have that event will actually be observed. We can look at it as a probability, as a frequency. It may be very qualitative, but it's getting at that idea of what's our degree of confidence that an event will actually occur. Consequences, we're talking about adverse impacts that are important to decision makers. So there may be some things that a system or a system of systems can do that we don't care about, the decision makers don't care about. We don't need to analyze that. On the other hand, we're looking to support the decisions that are of the system owners to change their system, and so the consequences are a key portion of understanding that. Threat is something that has a lot of different definitions depending on who's talking about it. Some people will talk about threats in a way as only being a malevolent outsider, like a terrorist or a criminal. Others will talk about threats to include some things like a hurricane or an earthquake as being a threat. There's a couple different definitions here. We have used both of them and find that the context of the discussion is usually adequate to distinguish between them. So in the first definition, we're talking very broadly about what a threat may be, to include both malevolent threats as well as circumstances, be they hurricanes or fires or even just broken pieces in a system. The second part of the definition there is talking about intention and capability of an adversary. Vulnerabilities are things that are characteristics of the design or implementation or operation that can be exploited by an adversary or disrupted by a natural hazard or a technological failure. So they are the things that the threats operate on to produce consequences. And then we talked about risk previously. It's the potential for realization of unwanted or adverse consequences. Those are the basic definitions that we will use. There's a bunch of modifiers that we will also use with respect to these, and I want to talk about those for a minute. So we can talk about scenarios, risks, likelihoods, threats, vulnerabilities in terms of these statements as well. We talk about what we give to a decision maker. We can do identification of risk or likelihood or scenarios, analysis, or assessment. So for identification, we're talking an initial step of recognizing what's there. Analysis is a critical examination, and an assessment takes a step back and judges the extent or the importance of the risk or the scenario or the likelihood or the vulnerability. Those are the pieces that we roll up into risk that we present to a decision maker. The decision maker then has to figure out how to manage those risks. And risk management we talk about, or consequence management, or threat management, whatever we're managing, is first of all understanding the risk or threat, and then taking appropriate actions to either do something about it or accept it. Try to control it or understand it so that if what we're worried about does actually occur, we're not surprised by it. So management can occur by accepting the risk or the threat or the vulnerability, or we may decide to mitigate it, to do something about it. We may decide to just monitor it. We need to understand it better, check it systematically on an ongoing basis so that we can determine whether we want to refine our assessment and mitigate it or just accept it. So these definitions have worked well for us in communicating. A key for you as working on risk analysis is to understand what other people mean when they use particular words, because they may not mean exactly the same things that we mean with these words. So talk to people, understand what they mean, and otherwise you're likely to end up in a kind of a circular conversation. So to review, risk revolves around three questions. What could happen, how likely is it, and how bad is it? Our goal is to understand the universe of possible scenarios and to help make well-informed management decisions. We talked about completeness a little bit before, but we're only going to go into as much detail as is required to understand, to support particular decisions. And so we're going to go into a different level of detail depending on what is appropriate to support that decision. The starting point for risk analysis is generally to identify consequences. We can start this at just a real casual level by saying, why does anyone care about this system or function or issue? There are a lot of things that could happen as a result of it, whether it's that bad things actually happen, like I've listed here, lost wages, repair costs, liability, death, sickness, environmental damage, socio-political effects, could be as a result of the operation or failure of a system or system of systems. But consequences don't just have to be bad things happening. They could be good things fail to happen. Each of the systems is designed with in mind the idea that it's supposed to accomplish some good purpose. And failure to provide that good purpose can be just as much of a consequence as actual costs incurred. So if we can no longer use a system to its beneficial purpose, that is also a consequence. And we can quantify that in the same way as costs or opportunities missed or those kinds of things. So as we look at consequences and identify consequences, these are the kinds of things we are typically looking at. There's also indirect consequences, especially when we're talking about system of systems kinds of models. There's the direct consequences, say if we're talking about an electric power utility. There's how long the power was out, how many people were affected, how much it's going to cost to repair it. There's also indirect consequences, such as the spoilage of food in people's refrigerators or traffic accidents that occur because signals are out and so forth. And you can move further and further out to look at indirect consequences. So there are costs associated with businesses that had to close, business transactions that could not occur, financial losses, and so forth. The indirect consequences can be economic. They can be changes in citizen or consumer behavior. We saw that after the 9/11 attacks when people stopped flying, and so we had to bail out the airline industry. It was an indirect consequence of an event that actually happened. Cascading impacts, if electric power goes out, for example, you may have consequences in the telecommunications sector, in the banking sector, with water, and so forth. So there can be a cascade of impacts from one system to another. Finally, loss of faith in government is an indirect consequence, but it can have really profound impacts. After Hurricane Katrina, people lost a lot of faith in the United States government's ability to protect them or to make them whole after a major catastrophe, and so that has affected people's perception of government. It affected the structure of the government itself in some cases. So there are the indirect consequences can sometimes be greater than the actual consequences themselves. Another key aspect of consequences is the time frame. When do they occur, and what's their duration? We can talk about immediate consequences. For example, an explosion produces immediate consequences. There's destruction, possibly death or injuries, resulting in it's very immediate. On the other end of the scale, if we're talking about, say, a radioactive waste disposal site, it may be 10,000 years before the radioactive contamination, the radioactive plume, migrates from the source to an underground water source where it might get into the water supply. So that's going to have an impact on people's decision making. We need to understand that as part of our analysis. Similarly, the duration of the outage, or duration of the consequence. On one end of the spectrum, we have permanent consequences, deaths and so forth. There may be consequences that last only for seconds. For example, in the telecommunications industry, if a particular cable goes out for only a few seconds, the duration may be short, but it may have a very high impact on some particular industry. So we need to take a look at the durations that are involved as well. Risk is not linear in these factors in terms of when it happens or how long it happens. Let me give you an example. In the telecommunications industry, we can take a look at the number of people affected by a telecommunications outage and the duration of the outage. If it is very difficult to compare, for example, an outage that affects 1 million people and lasts for a minute with an outage that affects 10 people and lasts for 6 months. If you were to multiply those two together, the number of people and the duration together, you'd get kind of similar numbers there, and yet our human perception of those consequences is very different. So there's nonlinearity there. We have to understand that as we are communicating to decision makers, that not all consequences are the same, even though we might multiply them out in some way and come up with equivalent point values. There's human perception involved in that as well. Another key aspect of understanding consequences is who is affected. People are much more accepting of consequences if they come to people who are deliberately seeking or deliberately accepting those risks. If they are knowledgeable about them, or being a thrill seeker and get hurt in that situation, they're much more willing to accept that, as opposed to somebody who is, say, in a distant place, who's just a member of the general public who hasn't had any choice in the matter. In some cases, consequences can affect people who are very distant, even in foreign countries. A good example of that is the Chernobyl nuclear accident. It was first detected by people outside the Soviet Union, and there's radiological contamination that happened very distant from the site of the reactor and in different countries. So the key issues here in terms of how people feel about risk are the degree of control that they perceive they have over that risk, and the degree of benefit that they understand that they're going to receive from that. So I've put down here a kind of a hierarchy of risk acceptance. At the top, people are very, very willing to accept risks that they have deliberately sought out, thrill-seeking, parachutes, hang gliders, and so forth. People understand that there are risks associated with that, and they're accepting it for the thrill of it. At the bottom end of the scale, you see that there are risks imposed by others with no perceived personal benefit. Those kinds of consequences, people are very likely to fight back against. It all has to do with the degree of control they understand they have over those risks and the perceived benefit. That's why, even though the likelihood of death occurring as a result of auto travel is significantly higher than the likelihood of death from air travel, people are much more willing to accept the risks of auto travel because they perceive that they have significant control over that risk, over those consequences. We need to understand these as we work toward risk assessment and have identified the consequences. So we've talked about why people view behaviors of systems as being bad or consequential. Let's talk now about metrics, because if we're going to compare among risk alternatives and among scenario alternatives, among alternatives for how we're going to configure the system, we need to be able to answer the question of how much for each of these consequences. Some kinds of consequences, it's very easy to understand in terms of quantitative values. Numbers of dollars, deaths, injuries, and so forth are all things that we can compare on a numerical basis and say one particular scenario is worse than another particular scenario. Now, got to understand that the perception is nonlinear, but indeed we can compare them on a numerical basis. There are a lot of other kinds of consequences that are not numerical, and so we have to compare them on a verbal basis, maybe a point system or a ranking. So in order for these to work well, we have to have a clear definition of what those anchor points are. When we say a high consequence, are we talking something that would be 5,000 deaths, or are we talking about 5 people who are injured? So a clear definition of what each of the terms means when we're doing verbal, qualitative consequence metrics is key. Sometimes we will do things in terms of a point system. Analytic hierarchy process is well known for putting together a point system to rank different alternatives. That's fine, again, as long as we understand what the relative weighting, the relative magnitude is among the different verbal scores that are given. Rankings are another way to look at things where we don't necessarily have to pin down exact definitions of things. We can rank different scenarios or different consequences, different alternatives in order from greatest to least or least to greatest. And that helps us avoid the need to precisely define the terms. And there's some fuzziness involved in these terms that in terms of the definition of high versus low that we can maybe get around with a ranking system. Now, a problem that we frequently have in risk assessment is that consequences aren't just one consequence for a particular scenario. For example, if a nuclear power plant has an accident, we don't have just one metric for how bad things are. There's the metric of how much radioactive material was released, how many people died, if any, how many people were injured, if there's going to be latent cancer fatalities. There's the size of the area that was contaminated, in addition to things like how much milk had to be interdicted, food, and so forth. Now, each of these consequences can be measured numerically. How do we add all of that up to say, here's how bad that particular scenario was? Well, that in fact is a value judgment, and if I were to ask 10 different people which of those many consequences were more important and by how much, I would probably get many different answers. So adding up the consequences across disparate types is very difficult to do. Some people will convert it in terms of a society's willingness to pay into a dollar figure that can be added up. That's probably the best we have right now for working those kinds of issues. But most people, including the Nuclear Regulatory Commission, tend to look at consequences separately. So they'll look at the risks of fatalities and look at the scenarios that result in large numbers of or large amounts of area of land that have to be interdicted. They'll look at those separately and make their risk decisions by integrating them just emotionally rather than numerically. If we're going to use consequences. We spent time talking about what consequences are and what makes a facility or a system perform badly. What we want to do now is figure out what can cause those consequences. And a good way to start through the process of identifying scenarios is by using what I'll call the reporter's questions. If you remember when you were in elementary school doing probably a social science project, you looked at what kinds of questions do newspaper reporters ask? And there were 6 of them. Who, what, where, when, why, and how. And they form a good bridge for us to understand what scenarios cause particular consequences. So we can start with why. What are the potential consequences? Why do we care about the system acting in a particular way? Then from that we can often understand what it is we need to prevent, what situations we need to prevent, or what things it is we need to protect. So are there specific things there, assets, missions, information that we need to prevent, or do we need to make sure that certain things happen? Sometimes who does something can be very important. If we're talking about the authority to launch nuclear weapons, who does that makes a great deal of difference. We want to make sure that only the president has that authority. So who has the authority to do these things, and who can touch things can be a very important factor in developing scenarios. So a scenario may say that a particular person we don't want to does something to a system, and that causes the consequence that we fear. How people interact with a system is very important. From a safety perspective, if someone is trying to fix an electrical connection, how they do that is critically important. They take specific steps to make sure they aren't standing in water, for example. So how these interactions happen is key. Where is also very important. Certain things can only exist in certain locations or else they are a problem. We don't want chlorine gas existing out in the environment. We only want it in the tank where it's supposed to be. It's fine in the tank. It causes great consequences when it's in the wrong location. And when is another important part of setting up a scenario. Some cases, the order of events matters greatly. For example, if a fire starts after a gas tank is drained, it's not nearly so bad as if that same fire starts maybe before the gas tank is drained. So order and timing are critical aspects of the scenario. So as you can see, asking the reporter's questions here helps us start fleshing out what we mean by a scenario that can cause consequences. From there, we can move on to the different types of scenarios, fleshing them out in more detail to understand the specific consequences that may arise. A scenario, as we said before, is an outline or a synopsis of observed events or postulated events. It's a script, if you will, typically high level. We can discover these scenarios in a lot of different ways. They can be based on the reporter's questions that we just talked about. And when we use the reporter's questions, we may do it just by brainstorming. We may have a dedicated set of experts come in to help who know vulnerabilities and can act as an adversary force against us. We can also look for scenarios that violate best industry practices, because usually those practices have been developed over a period of time in response to some undesired thing that's already happened. They say, we don't want this bad thing to happen again, so we're going to make sure that it doesn't by putting in these best practices. All of those are good ways to establish scenarios. Two that are a little more intensive are simulation and logic models. For very complex, especially system of systems types of problems, we may run an may run a simulation, whether it's an agent-based model, a dynamics model, but the idea behind those are to go through the types of conditions a system can find itself in systematically, either by random means in an agent-based simulation or in a design of experiments kind of manner for a system dynamics model, to explore how this complex system behaves under the widest possible set of conditions and environments. So we can use simulations, look for those cases where the system behaves in a way that is that we don't want it to, where consequences are produced, use those scenarios as a basis for further investigation. Finally, we can talk about logic models, and I'm only going to talk about those very briefly here. We'll talk about those in more detail when I'm talking about some of the examples of risk assessment that we do today. But for systematic logic models, there are really two types. One is an inductive logic model, and here we reason from cause to effect. So we start out by postulating a series of initiating events or potential things that might cause consequences, and we follow them through to their outcomes. So we start with cause, move to effect. And there's a lot of methods for doing that that you can see here, HAZOP, failure modes and effects analysis, and I have some references for them later in the presentation. This is an inductive model because you're starting with a postulated initial event and looking to see where, inductively, where that can go. The other thing we can do is a deductive logic model. Fault tree analysis is the best example of a deductive model. Here what we do is postulate the consequences and look backwards from that to say if this consequence occurred, then this previous set of conditions must have already occurred. And we can decompose those effects into their root causes. It's essentially a formal root cause analysis, and from there identify all the different causes for a particular consequence. So we have inductive models, we have deductive models. In fact, both are used in risk assessment, and they are very complementary in the types of answers that they provide. And we'll discuss a little more of this later on. We've talked about what kinds of scenarios we can get, how we can develop scenarios, these scripts. The third part of risk is likelihood. So what bad things can happen, how bad is it, what can happen. Let's talk about likelihood. When we talk about likelihood, we're talking about an uncertain future event and what's our degree of confidence that that outcome will actually occur. Traditionally, for the mathematically inclined, this comes about through probability. And this is the probability that a scenario will occur, or else a frequency. There are other ways that we can look at this, though, verbally, like verbal descriptors of ranges of probability or frequency, and we can tie those to approximate probability values. So something like unlikely may be a 1 in 10 chance that it would happen. We can also rank order things just as we could with consequences. So we may not have statements about the actual frequencies among these different alternatives, but we may be able to say that this group of events is much more likely than that group of events, rank order them in such a way that we can make some important statements about them for risk. Finally, there are hybrid methods, and these are really just combinations of the other methods. So we can rank order groups of events and say we understand statistically that this what the likelihood is of some of these groups, and we can infer approximate likelihoods for some of the other events then by looking at where they fall with respect to the ones that we've actually been able to analyze statistically. Statistical analysis is an important part of understanding likelihoods. We may be able to analyze to statistically assess the likelihood of an entire scenario, for example, automobile accidents. We can look at data from the country and know very well not only how likely auto accidents are, but even how likely they are down to particular zip codes in the United States. In a lot of cases, though, when the events are rare or very high consequence, we can't know we can't do a statistical analysis because maybe the event has never happened or it happens so rarely that we can't make a statistical statement about that. So we can look at the various events that form this scenario, understand the likelihood of those individual events, then use the laws of probability and statistics to combine those values to understand the likelihood of the event or scenario that we can't measure directly. So, for example, we can look at the likelihood that a motor breaks, which may be one element of a scenario, and from that start the statistical analysis on a more complex scenario that we've never observed before. Expert judgment, on the other hand, is where many of the likelihoods for scenarios come from. We use it all over the place because in some cases it's all we have. There are many things we have to be concerned about when we're looking to experts to provide judgment on the likelihood of events. We have experts who are sometimes biased. Do you think that you're going to get an honest evaluation of the likelihood of failure for a particular component from the vendor? It may not be very objective. It may be biased. Underwriters' laboratories may be a better place to go for that. You may also get a similar biased likelihood from somebody who's an activist against your project. They may fixate on particular pieces of the scenario and be very biased in their judgment of the likelihood. But even people who are very well-intentioned, who are world-class experts in a very specific field, may sensationalize their particular part of analysis or fixate on their pet issue because since that's what they know the most about, that's what they view as most important. So we need to be careful about this as we look to experts to provide us with likelihoods. Now, when you work with experts, you're likely to get different opinions of the likelihood of particular events. And we have to deal with that. If we ask 3 experts, we may get 3 different opinions. One of them may be dramatically different from the others, and we have to be careful about dismissing the opinions of experts. Once we've selected an expert, we've selected them because we view them as qualified to give us an answer. If we qualified on the subject matter that we're asking them about. If we say they're qualified at first, ask them the questions, get back an answer that we don't like, and then try to disqualify them after the fact, that's not very fair, and it's likely that it's going to raise a lot of questions, very legitimate questions, about the analysis. So we need to be sure to pre-qualify the experts that we use and be willing to take the information that they provide us with. We need to be very careful as we gather data from expert judgment because even the techniques by which we go through and ask the experts the questions can bias the results and give us inaccurate information. So it's important for us to use very sound expert elicitation techniques if we gather information from experts. There are processes out there that are very specifically geared toward helping experts understand the issues and avoid biased results. And I have a couple of references here from Nuclear Regulatory Commission work in this area that it's reasonably accessible literature, and you should be able to get some good ideas about what to do and what not to do when working with experts and eliciting their input. As I mentioned before, we need to interview appropriate experts. We need to make sure not only that they know their subject matter well, but they should also know how the system that we're working with works, and not only how it should work, but how it actually works. Sometimes those are very different things. Then we need to understand how it actually works. We need to be very clear in motivating the experts, help them understand what it is we want to get out of them, because in some cases, if we're not very careful about how we pose the question, the experts may give us an answer to a different question than what we actually wanted to know. So experts will have their biases coming in as far as what it is they think you need to know. We need to help the experts understand the problem we are trying to solve, take plenty of time to help them understand that, and then we can get much better results. Finally, we need to be sure that we keep track of differing opinions and probe into why those opinions are different. They may be looking at different situations that you hadn't thought about, and we need to go through and maybe develop separate scenarios to address these two different cases that the experts have looked at. So we need to understand why the differences have occurred, record them, and understand whether they matter or not. We can look back into our models at the end and see whether the results are sensitive to those differences of opinion before we try to go either gain consensus or model them. I've talked a little bit before about anchor points. Quite simply, you need to be very careful to make sure that as your experts are speaking, that everybody knows all of the exactly what these words mean. So if we have a word like unlikely, we need to have them have an anchor point from which to work that, to be sure that everyone is communicating well. Finally, it's really important if we're putting together a list of things, ranking things in order, that there's frequent comparison among the rankings, because inconsistencies can creep in without even knowing it. And if we find those when we're talking to the experts, we can resolve them quickly. So expert judgment is an important part of the whole process of developing likelihood for scenarios, because frequently we can't develop likelihood just from statistics. We've got now high-level consequences that we've talked about. We've talked about scenarios that cause them. We've talked about the likelihood of those scenarios. The next thing to do is look back at consequences. We've made a loop here, and that's important because a particular scenario may not have the worst case possible consequences. So we've started with the consequences based on the fact that a particular system may, let's take an example, there may be people that might die as a result of a chlorine leak. We've developed a scenario to reflect that. We've understood the likelihood of that scenario. Now we can probe that scenario a little more deeply and see just how severe it is. So one scenario developed from this source may have a large sudden release of chlorine, whereas a different one may have a very slow long-term release, which would cause far fewer casualties. So we need to look back at the scenario and understand how bad each particular scenario is for each type of consequence. We need to do a detailed assessment of the scenario, use the skin metrics that we talked about earlier, and if necessary, expert judgment can come in here as well. The process for doing risk assessment then starts with consequences, builds scenarios, likelihoods, and looks back at consequences again. And so we can see from this graphic of the process, the questions we're asking, what can occur, how likely is it, how bad is it, really form an iterative process, because there is the feedback of we come to understand one scenario. As analysts, we look at it and say, wow, there's this other scenario that I didn't even think of. So we'll do this iteratively until we've gone into enough depth to believe we understand the system, understand its consequences, and can convey that to a decision maker for them to develop policy and to develop possible mitigation mechanisms. So we're looking at what is risk, How do we assess it? We've assessed it here, and now the decision maker needs to take our information and accept that risk or control it or mitigate it. The next thing we're going to try to do then is communicate the risks to a decision maker. That turns out sometimes to be the most difficult job of all, because most of the decision makers are not scientists. Oftentimes they're politicians or they may be managers. So we have risk that is needs to be communicated to them in a way that they can understand. It's a function of the scenario, the likelihood, the consequences, and it's in some ways a nonlinear function, so we have to figure out how to communicate that. The original way that risk was communicated, often by insurance companies, was annualized loss expectancy, which we discussed earlier. A problem there has to do with the fact that risk is nonlinear. The perception of risk is nonlinear. So saying that I have 10 deaths once versus 10 single death incidents are very different from the perspective of human perception. And annualized loss expectancy would treat those as identical risks. A different way to look at this is using the graph that's on the bottom of this screen. And this is notional. It's using verbal risk values in cohort groups. But the idea here is that things that have low consequences and low probability have low risk. They're to the lower left of the graph. And as you move to higher consequences and higher likelihoods, you get into more severe risks. So each dot in this graph represents a scenario that has been analyzed. High-risk scenarios are in the upper right-hand corner of the graph, and those would be the ones that a risk manager would need to understand most carefully in order to be able to determine how they were going to manage risk. The color coding is something that's agreed upon by the people who are doing the assessment and needs to be communicated to the decision maker. And there needs to be communication about not just the red and orange, say, colors here, but about what kinds of scenarios tend to lead to high-risk situations versus what types of scenarios lead to low-risk situations. That will help them understand how any mitigation they might attempt will, first of all, help the high-risk scenarios, but also prevent people from making low-risk scenarios inadvertently worse. There are other methods of communicating risk. We've talked about lists, rank ordering by consequence, by likelihood. Exceeding a screening criterion is something that is a little bit dangerous. The reason for that is best told by example. There was a facility, there was a Department of Energy methodology for understanding, for doing risk analysis on criticality of nuclear materials. A criticality incident is a very severe thing at a facility if it has special nuclear material. The method that they used went as follows. They said, no individual scenario can have a likelihood of greater than 1 in 10,000, or no facility can have a criticality risk, criticality incidence more likely than 1 in 10,000 per year. No single scenario can be of greater likelihood than 1 in 100,000 per year. But we believe that anything that is less than 1 in 1 million per year is not credible, so it does not need to be considered. Well, if you can imagine the types of games that were played with that, people would take a scenario that was greater than 1 in 10,000 and say, you know, really, this is actually 2 different scenarios, and they'd have 2 small variations in it, each of which was less than 1 in 10,000, so they would meet the criteria. Or they would have a number of scenarios that were in the low frequency range, but still greater than 1 in a million, and subdivide those. And by subdividing those, they removed them down to the level where they were considered not credible and didn't need to be considered in the analysis. So people were playing games based on the threshold in order to get acceptable results for their risk assessment. We need to be very careful when using screening criteria or thresholds, therefore, to make sure that we're not cooking the books based on the screening criteria. We can also cluster things by likelihood, consequence, or risk like we've done before, but the whole goal of this is to help the decision maker understand the potential unfavorable characteristics of their system. Which scenarios pose the greatest risk, and what can be done to reduce those risks. That's the whole goal of our risk assessment. Now, an important part of risk assessment is helping the decision maker understand not only the scenarios and likelihoods, but understand how much it is that we know about these scenarios. And that comes in through uncertainties. Sometimes there may be great uncertainty in a scenario's likelihood or maybe in the consequences. And the decision makers need to know those uncertainties because it's going to affect their decisions. Take, for example, those two scenarios that are pointed to on the right side of the screen. It's difficult to know which of those scenarios has a higher risk because one actually is all in the orange region, and one, the consequences were so uncertain about them that they range clear from green to red. So it would be a logical thing for a decision maker to take that latter scenario and say, I don't know if I should fix this or not. Let me study it further. That may seem like a cop-out, but in this case, it is something that can help them avoid spending money unnecessarily, and they're still doing something to manage that risk. On the bottom row here, we have something that is very uncertain as far as its likelihood, but really it's not an important uncertainty because it doesn't really affect risk. So while we don't know the likelihood of that scenario very well, it really doesn't matter. Providing this kind of information to a decision maker who has responsibility for both the well-being of the facility and the research that goes on to understand it better helps them allocate their research dollars in an optimal manner and help them decide whether they should spend their next dollar on fixing a problem or on understanding a problem better. Again, the key is to help the decision maker understand what it is they need to do. A key way of displaying risk information for decision makers is the cumulative or complementary cumulative distribution function. This has been used for many years because it contains a lot of data, a lot of information, and is reasonably easy for a decision maker to understand once they've had a little bit of orientation to it. In the curve on the right, it's called an exceedance frequency curve, which is another name for this CCDF. And it answers the question mathematically of what's the likelihood that the consequences are this bad or worse. So we have the vertical line from the consequence axis representing how bad it is. The horizontal line goes to the frequency or probability axis, and it shows the likelihood that the scenario is that bad or worse. Mathematically, from a probability standpoint, this is 1 minus a cumulative distribution function. You can see it there written in integral form for a continuous continuous consequence function. In practice, we do things typically for scenarios which are discrete. So I've listed here the procedure for generating a complementary cumulative distribution function for a discrete set of scenarios. We can sort them in decreasing order by consequence, and then we just start adding up the list, and we go for the nth point, we add up the likelihoods of all of the of all of the scenarios that have consequences greater than that value. And then the plotting is just the set of ordered pairs. This probability sum is the y value, and the consequence for that point is the x value. And so we start at the lower right-hand portion of the screen and of the graph and work back up to develop this exceedance frequency curve. What that means is that for every probability, or I'm sorry, for every scenario with a consequence value, we are adding up the probabilities of all scenarios that are worse than that one that we have our eyes on. Plot that point, go on to the next one, and so forth. It provides a very good way of communicating risk to decision makers, because one of the questions they will almost always ask is, what's the likelihood that, say, one person will die? Or what is my 1 in a million accident? How bad is that? And those things always can come from a complementary cumulative distribution function. We can see that from the graph here. We've got 3 different questions you can answer here. This is an actual complementary cumulative distribution function for a particular space mission. The red arrow answers the question, how likely is it that at least one person will die from cancer within 50 years because of this mission? We draw the vertical line starting from one person dying, go up to the curve, read off the ordinate value for that, and see that it's less than 1 in 10,000. Another question we can ask is, if a 1 in a million accident occurs, how many people will die of cancer within 50 years? And we can see from the blue curve there, we start out at 1 in a million, move over to the CCDF, and then down to the abscissa, determine what the value is there. So we see that there's a 1 in a million chance that 200 or more people will die of cancer within 50 years. Another way to look at this is with the green bracket. You can see in the upper right-hand corner of the graph there several other CCDFs from typical functions that typical man-made hazards, such as the failure of dams, hurricanes, mass transit, and so forth. What we can see there is that since the risks for this mission lie considerably below those other CCDFs, that the risk of this particular mission is far below other comparable risks that people deal with every day. That can be a convincing argument to a regulator. It's not always a convincing argument to somebody in the general public, because they will, again, look at the risk hierarchy that I talked about earlier and say, I don't see any benefit to this. This is beyond my control. Therefore, I don't feel that this is a risk that I'm willing to accept. Whereas for an activity that they want to be involved with, that may be an activity they decide to accept, even if it has exactly the same risk. So it can answer the comparison question. It can't answer the emotional question about whether or not this is something that will be acceptable politically and something that should be done. You can see, though, how powerful a CCDF is. A key, though, is in order to do a CCDF, you have to have actual probability or frequency likelihoods for each scenario. Sometimes we don't have those, and we can't use those. We can't use a CCDF for that. We talked about the different kinds of information that a CCDF can bring you. It's also very useful for regulators, because the way in which points are defined on a CCDF is very much like the way regulators think. A regulator will say, for example, the likelihood of at least one death from this activity shall be less than 1 in a million. Well, that's exactly the same as a number that we would get off a CCDF curve. So we can make that translation directly. A regulator may make 2 or 3 pronouncements of points like that, and we can look at those, place them on a curve, connect the dots, if you will, and now we have a risk acceptance surface. So anything that falls under that risk acceptance surface is approved. Anything that falls outside of that risk acceptance surface is not approved. It provides a very easy way for the regulators to think about the problem and for the risk assessment team to communicate back and establish whether or not they are complying with the risk regulations. We've talked about communicating risk with decision makers now. It's time to talk a little bit about risk management, because risk management is the whole purpose of risk assessment. Simply understanding the risks doesn't make a difference. The key aspects of risk management are first to understand the adverse conditions, and then we take actions to manipulate or control it, or we accept it. And we do that within the constraints of cost, schedule, and operations. The way we do that is by identifying risks, analyzing and assessing them, and only then can we manage them. Lots of different ways to manage risk, and they have to do with the likelihoods, they have to do with the three risk questions. So we can look at the consequences. What consequences can occur? Can we completely eliminate those consequences by, say, changing to the system to eliminate a hazardous material? Or maybe we can mitigate them, the consequences. Maybe we can't do anything about consequences, but we can reduce the likelihood of a scenario. Or we can interrupt the scenario before it has the chance to get into the causing a consequence. And finally, we can decide that we're going to accept the risk. Maybe we're going to monitor the process or buy insurance. So we can look at all three parts of the risk triplet: likelihood, scenario, and consequence. We can exert controls in all three of those areas to manage risk. And I challenge you, every time you need to manage risk, to look at all three of those. Typically, we get ourselves into a mindset where, for example, I only control certain aspects of my system, therefore I'm only going to look for particular types of risk mitigation options. Limiting your options in that way may mean that you're inadvertently cutting off risk mitigation options that you're not even aware of. So before you zero in on one answer, think through all the different parts of the risk triple. A key example here is in the security of high consequence facilities, like dams, nuclear power plants, and so forth. We may believe that the only way we have to control risk is to limit access to these facilities. So we're going to do a vulnerability and put up walls and barriers around these assets in order to protect them. In fact, if we look at likelihoods and consequences, we may be able to do things that we hadn't thought of otherwise to prevent the scenario entirely, remove the consequences, and so forth. So please don't limit yourself to particular scenarios before you start, particular risk mitigation technologies. Key here, as far as risk management, we need to understand the risks, and then we need to communicate those to the people who can mitigate them or manage them. Understanding the whole problem, optimizing the whole system, looking at the total life cycle, these are keys to system engineering that you've been learning about in other parts of this class. And a good reference to this is the INCOSE website, the International Council on Systems Engineering. Be sure you are doing good systems engineering when you look at risk mitigation. Oftentimes we tend to look at risk mitigation as band-aids to put on the system, as opposed to things that work through the entire system that we have to optimize on a system-wide basis. What sometimes happens then is that the fixes we put in for one risk inadvertently cause risk in some other parts of the system. So We need to understand it as a systems engineering problem, looking at the whole problem, looking at the whole system, and looking at the whole system life cycle. So to summarize here, risk assessment is an iterative process. It starts typically with consequence assessment, but it's not limited to a particular order of steps. It's the process of understanding likelihood of scenarios, severity of scenarios, and what scenarios can actually occur. We can do that in different orders as we discover things. The key is that it's a process. It's a disciplined process. We need to follow wherever the information leads to root out wherever the consequences are, the scenarios, the likelihoods, until we come to enough information that we can support a decision. Decision making is key. So there are often many stakeholders in a system. We need to document things so that all of the stakeholders in the system can understand where these risks came from, where the suggestions for improvement came from, and why the risk exists in the first place. People who have different disciplines or different parts of the system under their control may not understand the whole context. So our documentation is key to helping them understand why there's a problem and why something needs to be done about it. Risk assessment, we've talked about completeness. We need to understand the whole system and all of the different scenarios or types of scenarios in a risk assessment. Being systematic about how we go through the assessment is critical. There's no foolproof way to identify missed scenarios. If we have gone through our analysis without identifying a particular scenario, we may be missing a very important risk, and there's no way to tell whether that risk is important or unimportant, whether it's a high or a low risk. So being disciplined and systematic about how we look for consequences and how we look for scenarios is very important. I said before that this is somewhat of an art and somewhat of a science. How do we know when a risk assessment is complete? Because that seems to be part of the art part of risk assessment. The best answer I can give is twofold. Number one, when you have enough information to support well-informed decisions, and when you're reasonably sure that all of the relevant scenarios have been identified and examined. When we've gotten to that point, we've got a complete risk assessment. Being systematic about it helps us get to that point sooner with greater confidence. As you can see from what we've talked about, risk assessment is not something that we want to have the world's expert in a small, tiny domain doing. We need someone who understands the broad context of the system, conversant in many areas, to be able to look at the breadth of the system, understand the consequences, understand the scenarios, be familiar with that in order to develop scenarios, develop consequences, and so forth. A risk analyst must know his or her limits in order to perform an effective risk assessment. They need to seek out experts in particular phenomena. So a risk analyst may identify that if a particular part of a system, a particular pump breaks, for example, then bad things will happen. They can then go to the expert who understands that pump best, get information about the likelihood and conditions under which it might fail, bring that into the analysis, combine it with other things across the system to understand the context and whether or not that pump is really important to risk. So a risk assessor should be a generalist who knows their limits and can go talk to experts when it's needed to further inform the risk assessment. In the next lecture, we're going to change gears a little bit here. We're going to talk about different applications of risk assessment. I'm going to go through a number of examples very quickly, talking about what happens in risk assessment, what we care about, and how these different types of risk assessment vary from one another. We can talk about technical and non-technical problems. The process remains the same, the disciplined investigation of scenarios, likelihoods, and consequences. But you can see applications here ranging from safety systems to political decisions, financial instruments, environments, and so forth. There are a lot of domain-specific tools that exist to address these different consequences and systems. The process remains the same, and we'll discuss that in much greater detail in the next lecture.